Hello everyone, this is Chandrakant Mishra. Today we are going to discuss the GATE 2021 questions coming from the electronics devices. First question, which is question number 6 of GATE paper. A bar of silicon is doped with the boron concentration of 10 to the power 16 cm-3 and assumed to be fully ionized. It is exposed to light such that the electron hole pairs are generated through the volume of the bar at the rate of 10 to the power 21 centimeter minus 3 and second minus 1. If the recombination lifetime is 100 microsecond, intrinsic carrier concentration of the silicon is 10 to the power 10 centimeter minus 3, and assuming 100% ionization of the boron, then the approximate product of steady state electron and hole concentrations due to this light expose is. Here the concept is N minus N naught is equal to GPP and tau p. That is photogeneration rate and the lifetime of the recombinations. And this is the N, that is the carrier at steady state, and the carrier when there is no light, that is N naught, which is equal to GPP minus tau p. Tau p is the recombination lifetime and GPP is the photogeneration rate. Here we have applied the external energy, that is in the form of light. Another form of external energy that can be applied, that is electric field also. Similarly, you can write, because when the light falls on the bar or all over the bars, the not only electrons generate but electron and holes pair generate. So similarly for the holes, you can write P minus P naught is equal to GPP tau p. Right? What is the N naught and P naught? As it has been given in the questions that boron is 100% ionized. Boron is a trivalent impurities, so it is 100% ionized, means P naught is equal to Na, which is equal to 10 to the power 16 cm to the power minus 3. Then from law of mass actions, your N naught will be the Ni square upon Na. These are the thermal equilibrium carriers, P naught and N naught. So N naught is equal to Ni square upon Na. So Ni already has been given, that 10 to the power 10. So this will be 10 to the power 20 upon 10 to the power 16, which is equal to your 10 to the power 4. Now come to the right hand part, that is GPP tau p. GPP already has been given. See here, electron and hole pairs are generated throughout the volume of the bar at the rate of 10 to the power 20 centimeter minus 3 second inverse. So GPP is the 10 to the power 20 into then tau p, that is 100 into 10 to the power minus 6. So how much it is coming? 10 to the power 16. So now you can calculate what is your P, what is your N. So P is equal to P naught plus GPP tau p. So your P naught is equal to 10 to the power 16 into GPP tau p is the 10 to the power 16. So sorry, plus so you will have 2 into 10 to the power 16. Now come to the N. N is equal to N naught plus GPP tau p. So your N naught we have just now calculated 10 to the power 4 plus 10 to the power 16, which is same as 10 to the power 16, because 10 to the power 4 is very small number compared to 10 to the power 16. And these are the steady state values. So the question is the approximate product of steady state electron and hole concentrations. So P into N. So P is 2 into 10 to the power 16 and N is the 10 to the power 16. So 2 into 10 to the power 32 is the right answer, and your option D is correct answer. Let us move to the next question. Here the question is question number 7 of the gate paper. The energy band diagram of p-type semiconductors bar of length L under the equilibrium conditions, that is Fermi level EF is constant, is shown in the figure. The valence band EV is slope since doping is non-uniform along the bar. The difference between the energy level of the valence band at the two edges of the bar is delta, as shown in the figure. If the charge of the electron is Q, then the magnitude of the electric field developed inside the semiconductor bar is. Okay. So this is the concept of non-uniform doping. As you know that two concept here applies, that is from energy to voltage. How will you find? That is E upon Q, that is charge of, or you can say the electronic charge. I am not talking about the charge of electron here. So electronic charge. And then from once you have found the V, then you need to find the electric field. This is your energy. Okay, the electric field is the negative gradient of V from the theory of electromagnetic. Okay, so now come to this picture. They have already given. If you can write the equation for this EV, you can easily find the potential because it has a definite slope. So equation of a straight line here. This is your EV axis. This is your Z axis. So the equation of this EV will be EV minus EV0 is equal to, that is point and slope form, Y minus Y naught is equal to slope into X minus X naught. Remember from your intermediate classes. So EV minus EV naught is equal to slope. What is the slope of this line? Del upon L. Very clearly it is shown in the figure. So del upon L. Then this X, because it is Z axis, single Z axis. So Z minus 0 because it starts from the 0. But we don't know where it starts, the EV, where it starts. So I wrote the constant. I wrote the constant EV naught. So EV equation is simply EV naught plus del upon L Z. Now come to this picture. See the how bending occurs here. In the left side it is deep into the bottom, and the right side in the up to the top. That is, it is at the higher energy, okay, for electron, and it is at the lower energy. If you have studied from the basic, when electron, let's say electron is here with some energy E naught. When electron is here, okay, with energy E naught. If you apply an positive potential to this electron, what happens to this energy? Energy of electrons becomes, because from the basic theory of electromagnetic, you know, energy is the charge, electronic charge into the voltage. But electronic charge, that is the electronic charge for the electron, is a minus E, and the voltage, suppose you have applied the positive potential, that is E0 minus EV. That means whatever the energy is here, now energy is lowered. Energy will be lowered for these electrons. If you, in the same analogy, if you apply negative potential to this energy, these electrons, the energy will be increased. So exactly same case. So we found the voltage from energy to voltage in the reverse way. So voltage will be the EV upon negative of electronic charge. So negative of electronic charge, that is electronic charge, they have not taken E but Q. So negative of Q. Okay. So you have minus EV naught upon Q minus del upon L Q and Z. And then last action is here to find electric field E equal to minus del V, that is the gradient of V. Here is the one dimensional only. So minus d dz d upon dz to V and az, that is the direction of the electric field. So this is the constant. The differentiation of this is 0. This is a linear function with the z. So ultimately you will get del upon q and L and az, and it has asked the magnitude only. So magnitude will be the del upon q L. So answer is option A. So as you are writing the gate question, you can directly, because it has nothing to do with the sign or direction, so you can directly plug this and find the answer within a minute. So this is the procedural, so that you can understand the concept behind. Okay, let's move to the next question. So let us move to the question number 30 of the GATE paper 2021. For an N-channel silicon MOSFET with 10 nanometer gate oxide thickness, the substrate sensitivity, that is del Vt upon del magnitude of Vs, is found to be 50 millivolt per volt at a substrate voltage magnitude of Vs is equal to 2 volt. Where Vt is the threshold voltage of the MOSFET, assume that magnitude of Vbs is very greater than the 2 phi b. What is the phi b? Where q phi b is the separation between the Fermi energy level EF and the intrinsic level. Okay, Fermi potential energy EFI in the bulk. Parameters given now: electric charge, vacuum permittivity, then relative permittivity of the silicon, and relative permittivity of oxide, and the doping concentration of the substrate. Okay, I can say this is the actually tough questions. If you don't remember the exact formula, even I had appeared for the GATE 2021, I could have left for the next attempt or next round of the question doing, because I don't normally memorize all the formulas, big formulas, but definitely we can calculate with certain by applying the certain easy formula. We know that this is a n channel, so obviously the substrate is the p, and if you know the structure of the MOS, NMOS, you know, like this. This is your metal side, this is your oxide, and this is your semiconductor. Why I am drawing like this, you'll understand, because to give a polarity to the charges. As you know that gate voltage or threshold voltage, that is gate voltage, is always positive, so this is the positive charge or unexposed charge. Then here your negative, that is the trivalent impurities, unexposed, sorry, exposed trivalent impurities like boron, gallium, indium, and this distance is the maximum, because threshold voltage you are calculating, the maximum distance is the xdm. Okay, and this is your qm. So for the time being, I will assume that there is no trap charges in the oxide. So as for the charge neutrality, okay, let's say this is the qs, total charge per unit area. Qm plus qs is equal to 0, so qm is equal to minus qs. What is the qs? You know that is electronic charge, and this is the exposed ions of the trivalent impurities ions, so q, na, and x dm, negative, because these charges are negative. Now come to the threshold voltage. The threshold voltage is the VTH is equal to phi ms, that is the Fermi level potential difference, that is the work function difference between the metal and semiconductor in terms of potential, phi ms plus 2 phi Fp, that is the Fermi potential of p-type semiconductor twice T, that is the same here given as a 2 phi b. Okay, that is phi b is same nomenclature as the phi Fp, because p-type semiconductors, that is substrate is the p-type, then plus oxide voltage VOX, right? So these are the two constants. So I can, how can, because I need to find the rate of change with respect to substrate and bulk. Obviously it must be reverse voltage, so I can write a constant like k. Okay, this is constant to denote this. VOX, you know, the from the network theory, that is the qm, voltage across the capacitors, because capacitors is formed by the semiconductors and metal and oxide. COX, oxide capacitance for unit area, and because charge also coulomb per unit area. So this constant k, so to differentiate it, I'll write k naught. Okay, k naught plus qm, but what is the qm here? Qm is equal to minus qs, but minus qs and this qs, okay, one step I'll write, okay, minus qs upon cox, which is k naught minus, see here also minus q na xd, so k naught plus q na xdm upon cox. Now question is xdm. See, because I don't remember the formula. Okay, I am seeing the formula, but if you are stuck in the exam hall, still you have time, right? But this is a formula which normally you can remember, but sometimes you most likely to forget, right? But this is the easiest way you can do it. But one thing we know that from the that is the semiconductors PN junctions, that is your built-in potential, right? What is the built-in potential for that is n plus p junction, which is equal to E upon 2 epsilon Na. Okay, E upon 2 epsilon Na, then that is the width square of width, right? So same way, when W equal to x dm, your phi Fermi potential will be the twice of the this is the phi is the surface potential, sorry, this is the surface potential. So surface potential will be the twice of Fermi potential. Now you can eliminate this you can eliminate this W. Okay, so what will this, okay, this W is equal to x dm. So and phi surface is equal to 2 phi fp is equal to E 2 epsilon. This epsilon is for the silicon, okay, because you will also use epsilon for epsilon for the oxide, also for the finding the capacitance, that is oxide capacitance. So 2 pi p E 2 epsilon silicon Na and Wi is the x dm square. So finally we can find the x dm is equal to 4 phi fp into epsilon silicon, okay, and ENA root over. So finally plug these values, so you can find the VTH. So VTH is equal to K naught plus, you see that, okay, one step I'll do, 4 phi fp epsilon silicon upon ENA, okay, 1 upon Cux, don't leave it, 1 upon Cx into Q NA x QNA, because for XDM we have replaced this one, okay. So next will be the, so your VT equal to VTH equal to K naught plus 1 upon COX, then you can see that, okay, same E or Q is the same. Here I have used E, electronic charge, they have also used the Q as a electronic charge as per the question. So you can either you change from here, or otherwise you will ultimately you will know it, okay. So you will have 4 phi fp epsilon silicon, okay, 4 phi fp epsilon silicon, then Q, then Na root over. This is actually a threshold voltage, but now they have applied the substrate voltage, that is VSB, obviously the reverse voltage it will be. So that's why they have given VBS magnitude. VSB is the positive and VBS is must be negative. So negative magnitude is the positive. So you know that threshold voltage when you apply the substrate voltage will become COX. So 2 epsilon silicon Q Na root over, because here is the twice of the Fp is your surface potential. So root over of twice of phi Fp plus VSB or VBS magnitude. This is the dependency of threshold voltage with the all other factors and including the substrate and the source and bulk voltage. Here the S is not, if you have told before the substrate, okay, this is the substrate and source voltage. Here for the substrate they have designated as the bulk, and S is for the source. So source and bulk voltage. So now take the differentiation dVt upon dVBS or SB, because this is a magnitude, it will not affect. So 2 epsilon silicon Q Na root over upon COX. Okay, and you know simple differentiation, this is your constant. So 2 phi Fp plus VSB magnitude root over, and as you know the differentiation with respect to this will be half, okay, another half, and the condition they have been given that VSB is very greater than the, that is your VSB magnitude very greater than twice of phi Fp. So finally these values will be the 2 epsilon silicon Q Na COX and 2, okay, then root over of okay, root over of VSB. This is the, because this is the very greater than this, so ultimately you got the this result. Now plug the values. So now we can plug the values. Okay, we have missed this one. Okay, so they have been given like this. These values they have been given the del Vt upon del VSB, and all this value we need to find the, so take the square of both the side, okay, so that it will be uh, okay, one second before squaring, just a little bit of doing these things. Okay, you can take the square, that is del VTH upon del VSB, this side square is equal to 2 silicon Si Q Na, okay, Na, then 4 COX square, then VSB magnitude. Okay, just write the, because VSB also positive here, but here they have been given VBS, so need not to worry about this. So this has been given as the 50 millivolt, so 50 into 10 to the power minus 3 square. Okay, so you have 2 epsilon silicon Q Na 4 COX is the epsilon OX upon TOX square. So epsilon OX upon TOX square VSB. Okay. So then next step, so you can you can see that one of epsilon 0 is getting cancelled with the epsilon silicon. So see, I am going to write this 2 epsilon silicon. So epsilon 0 from the top is getting cancelled, so we have only epsilon r silicon, epsilon r relative permittivity of silicon r, then q, then na, then 4. I have gone 1 epsilon 0 here, from here gone epsilon 0, then epsilon ro oxide square, then TOX square, then VSB is the, how much was the VSB? 2 volt. So this side will be your, when you square it, you will have 225, and already you have gone 10 to the power minus 3 with 1 0, you have gone 10 to the power minus 2, 25 into 10 to the power minus 4. Okay, then you have into 8, because 4 into 2 into 8, right, into epsilon naught, then epsilon r naught square. This much has gone to the multiplications. What are the for division to find the Na? Division this and this. So you have that you have 2. Okay. Okay, one second. Right. Pi is b. Okay. So you have epsilon r for silicon, then you have q. Okay. Then you have your 2, then into this one, TOX square, which is same, which is equal to NA. So now put all together now, 25 into 10 to the power minus 4 into 8. Epsilon naught they have been given 8.854 into 10 to the power minus 12. But here every calculation is in the centimeter. So you have to convert into the 10 to the power, that is the 10 to the power minus 12 farad per meters. So always remember the device centimeter to the power minus q, the concentration is used. So you need to convert. So 8.854 into 10 to the power minus 14, right? That is farad per centimeter, right? Then epsilon r naught, that oxide capacitance square, so which is equal to how much? That is a relative permittivity of the oxide, which is given as the 4. So 4 square is the 16. Then come to the 2 into silicon they have been given 12, the relative permittivity. Then q 1.6 into 10 to the power minus 19. Then TOX, how much is the TOX they have been given? So TOX has been given, let us check. TOX they have been given as how much? 10 nanometer. When you convert into the centimeters, so you have 10 to the power minus 6 centimeters. Okay, because 10 nanometer, so 10 to the power minus 6, and the square of that will be the 10 to the power minus 12. Okay, so the process is just multiply this, and this. Okay, right? 25 into 8 into 16 into 8.854. So with virtual calculators you can calculate. So 28.33, okay, into 10 to the power 3. You'll find this. Then, and here is the 10 to the power minus 14, here is the 10 to the power minus 4. So 10 to the power minus 18. In the bottom you will have 12 into 224 into 1.6. So when you multiply 38.4 into 10 to the power minus 31. So when you divide 28 upon 38.4, you will get 0.7377 into your 10 to the power minus 18. Okay, ten to the power minus 18, this is the negative, is the 10 to the power minus 18 into positive, this is the 10 to the power 3, and when it goes to the numerator is 10 to the power 31, so 10 to the power 34. So you get 0.7377 into 10 to the power 16 centimeter minus Q. So ultimately you will get Na is equal to 7.377 into 10 to the power 15. So this is the answer. See how lengthy it is. So 7.37 only single answer is correct. ऐसे क्वेश्चन दो चार आ जाए ना फिर गेट देना भूल जाओगे. Let us move to the next question. Question number 42. Okay, one thing, one advice I want to tell you everybody, because please don't fight with the question in the GATE exam. The simple principle is this question that we have done before. That is question number 30, I think. See, if you fight, because some people are so much emotional with the subject. This is my the favorite subject. I have learned from the so big professor or the golden teachers who have taught me all these things concept. I have to do it. Okay, you can do it, and you are going to, if some mistakes, then again recalculations, and ultimately as fast as you do, it will take at least 7 to 8 minutes, even though you can remember the formulas correctly. It will take 5 to 6 minutes, and if you done the mistakes, if it is not matching, then again you will do. So my basic idea of saying this is, do not fight with the question or do not be emotional, because your main motto should be attempt more number of questions correctly to get the most score. Nobody is going to award you a gold medal or anything for doing the toughest question of the GATE paper. Just remember it. Ultimately, at the end of the day, what matters is your numbers on the board. Remember that. Next question, question number 42 of the GATE paper. So here a silicon PN junction is shown in the figure. The doping in the P region is the 5 into 10 to the power 16, and doping in the N region is the 10 into 10 to the power 16. Okay, the parameters are given: built-in potential 0.8 volt, electronic charge, okay, and blah blah blah. So P, the length of the P side is the physical length 1.2 micrometers, and physical length of N side is the 0.2 micrometers. The magnitude of the reverse bias that would completely deplete one of the two region P or N prior to the other, rounded up to 1 decimal places. Okay, this is somewhat straightforward, though big calculation also involves, because built-in potential, permittivity, all these are there, but not like the previous one. You keep on calculating COX, all these things. Okay, so the question is how to decide which one will deplete first, because they have not given the because the doping is not same, and doping, if doping would have been same, then we can blindly say that N side will deplete first. But here the question is who will deplete first. That is the relations we know. W N N D is equal to W P N A. That is W N upon W P is equal to N A upon N D. What is the N A N D? P region is the 5. Okay, 5 into 10 to the power 16, and your ND is equal to 10 into 10, 10 into 10 to the power 16, so you get 1 upon 2. That is your WP is equal to twice of the WN. Okay, so deplete, you can check from this side or this side, it's not ISO. Complete deplete, let assume that I am not sure, let assume that N side is completely deplete. Complete deplete means 0.2 micrometers, so WP will be the, at that time, 2 into 0.2, that is 0.4 micrometer, because it is already given the 1.2 micrometers. So our assumption is correct, and that time W will be the WP plus, when the it is completely deplete, so WP and your WP will be W equal to WP WP and WN, so zero point 0.4 plus 0.2, that is 0.6 micrometers. So readily convert into the centimeter also, because we'll need to plug in somewhere. So 0.6 into 10 to the power minus 4 centimeter, right? This is the depletion width, total depletion width, where the N side will completely deplete. As per the question, we need to find the potential. But here the question is, it is not that much straightforward. Now we can put the values and then do that. But they have not given the W naught. That is the, what is the depletion with the width at the equilibrium or at the built-in potential. For that we have to plug in the formula. So for the formula, again, I don't remember exactly W, but I remember this phi bi, or built-in potential. Phi bi I remember this, and I only circulate, or you can say recalculate, to or rechart the, analyze and rechart the other relations. So I know this, that is E upon 2 epsilon. This is the constant term for the this, then potential. So Na, because the here no one is the heavily doped, so Na Nd upon Na plus Nd, and W square. Okay, so phi bi has been given 0.8 volt, E 1.6 into 10 to the power minus 19, and 2 epsilon. So plug all these values. What are the epsilon? 2 epsilon r is the 12. Okay, then epsilon naught is the 8.854 into, again, 10 to the power minus 14. So everything is in the centimeters here, right? Now come here, Na Nd that is a 50, 10 into 5, that is a 50 into 10 to the power 32. Then their addition 15 into 10 to the power 16. So from here we get 0.8 is equal to 0.8, that is, you can cut it here, 1 second. Okay, so multiply this 16 into 10, 1.6 into 10, that is your 16 into 10 to the power minus 19, okay, into 32 minus 16, that is the 10 to the power 16, and W0 square. Okay, here because we are calculating W at equilibrium, so W0 here, W0 square upon 2 into 12 into 8.854 into 3. Okay, so 12 into 2, 24, 24 into 3 is 72. 72 into 8.854 into 10 to the power into 10 to the power 14, minus 14, W0 square. So one step more, then little bit simpler, that is your 16 upon 72 into 8.854 into, so when it is go to this 5, that is 14 plus 14 minus 19 plus 14, so minus 5, then 10 to the power, that is 10 to the power 11, minus 5 plus 16, that is 10 to the power 11, W0 square. So finally you found the W0 square is equal to 0.8 into 72 into 8.854 upon 16 into 10 to the power minus 11. So 10 to the power minus 11. So finally when you divide 0.8 into 0.72 into 8.854 upon 16, you will get the 31.8744 into 10 to the power minus 11. So I can round off, so 0.32 into 10 to the power minus 9. This is the W0 square. So first concept we have already used, and second concept is V1 upon V2 is equal to W1 upon W2 square. So V1 your 0.8, V2 0.8 plus VR, reverse bias voltage. W1 already we have calculated, W1 square, that is 0.32 into 10 to the power minus 9, and fully depleted, just remember we just before we have calculated, I told you that it will be used later on. 0.6, that is a 0.6 is a W2, that is a W, that is the total depletion with the completely deplete the one of the region, that is W, that is same as a W2 for this for us. So 0.6 into 10 to the power minus 4, when you square it, 0.36 0.36 into 10 to the power minus 8. So we have 0.36 into 10 to the power minus 8. So finally what you will get when you divide this 0.32 upon 3.6. So just do a cross multiplications, okay, or you can further like divide by 2. Okay, you can do the division of 4, or you can directly multiply 0.8 into 0.36, which will get the you get the 2.88 equal to 0.32 into 0.8, so you'll get 0.256, then plus 0.32 VR, 0.32 VR. VR will be 2.88 minus 0.256 upon 0.32, and you will get 8.2 volt. This is the reverse bias voltage required to completely deplete one of the region, that is N region of the given device. So this is relatively doable, need not to worry about this question. This is the typical gate question, but that was somewhat at least they should give the COX, I feel so. Anyway, it is IIT to decide, not me. Okay, hopefully you can go through these questions and learn some concept. See you in the next class of analog. Thank you for watching the video.